Hi, today we will be discussing Lab 5 of Physics 2212, Magnetic Braking with Faraday's Law. In this experiment, we will observe the real-world effects of Faraday's Law by dropping a magnet through a conducting tube of aluminum foil. The primary goal of this lab is to use GlowScript to model the experiment and compare the experimental and theoretical time that it takes for the magnet to fall through the tube. Before proceeding, it's important to understand the fundamental physics principles behind the lab. First, Faraday's law states that a changing flux produces Curry electric fields and induces a current that produces a magnetic field and force that opposes the magnet's motion. The change in flux with respect to time is also the EMF associated with the induced current. The current can be solved for by dividing the EMF by the resistance. The third equation is used to find the magnetic field of a dipole, and the fourth equation is used to find the magnetic force of a wire. Since the magnet will be falling, we must also take into account the force of gravity, and the last two equations are kinematic equations that we will also use in the code. Here are the initial data and measurements from the experiment. The length of the tube of aluminum foil was 0.304 meters. The width of the foil on the tube was 0.005 meters. The inner radius was 0.015 meters and the outer radius was 0.02 meters. The mass of the magnet is 0.0241 kilograms, and the dipole moment of the magnet was 3.43, which was determined in Lab 3. The average time for the magnet to fall through the tube was 0.84 seconds. To simulate the forces experienced by tape B, this model was coded using GlowScript. The graph on the left shows the velocity of the magnet as a function of time as it falls through the tube. The image on the upper right shows the tube with the magnet halfway through. The red rings are where the current is flowing counterclockwise when viewed from above, and the blue rings are where the current is flowing clockwise. The direction of the current is determined by using the right-hand rule. Based on the code, the magnet should theoretically take 3.763 seconds to fall through the tube. Here is some of the code that was used to make the model. The first function shows the calculation of the magnetic field of the magnet. The second function calculates the change in flux with respect to time for each ring. Both of these functions use some of the equations that were shown earlier. In this part of the code, I calculated the magnetic field of each ring by using the function on the previous slide, which was then used to calculate the magnetic force on each ring as the magnet falls. The net force is the sum of the magnetic force and the gravitational force. The last two lines use kinematic equations to update the velocity and position of the magnet. Reducing the resistivity of the conductor would increase the induced current, which would also increase the magnetic force, causing the magnet to take a longer time to fall through the tube. If there were holes or slots cut into the tube, this would effectively shorten the tube and where the rings would have current, which would decrease the induced current and the magnetic force. Flipping the magnet around should not affect any of the dynamics of the system. The experimental time to fall through the tube was much less than the theoretical time, because the aluminum foil on the tube in the real-life experiment was not very thick. The velocity time graph shows that there were no acceleration while the magnet was falling through the tube, which means that the magnetic and gravitational forces were balanced. Thank you.